Hello everyone. What we're doing today is section 7.1, sampling error and the need for sample distributions. Um, we studied there at the very first of the year why a census is not a very practical way to sample. We talked about the money involved and the time, that a lot of time sampling um, can represent the distribution and can represent the population, and we can kind of get the idea we need from it. However, it's not very practical for us to think that sampling is going to give us exactly what the distribution actually is. It's going to give us exactly what the population says. Because what we have is in most samples that provide data for a portion of an entire population, you can't expect for it to be accurate. You got to anticipate some kind of error because we're human. So we call this error sampling error. Okay, and it's basically going to be our difference between our sample and our population. Okay, so let's look at this example. The Internal Revenue Service publishes annual figures on individual income tax returns. For the year 2005, the IRS reported that the mean tax of individual income tax returns was $10,319. In actuality, the IRS reported the mean tax of a sample of 292,966 individual income tax returns out of a total of more than 130 million. So they gave us a sample, basically, is what they did. So what we want to do is, first of all, let's identify the population under consideration. So what are we looking at? Well, we're looking, the population here just happens to be all those who filed an individual income tax returns. All individual tax returns. Okay, that happens to be our population. Well, what's the variable under consideration? It's the tax, the amount, the money. Okay, the amount of money that it's representing, the mean tax there. Is the mean tax reported by the IRS a sample mean or a population mean? Well, this is a sample mean. Why do we know that? Because they didn't do it out of the whole population of 130 million. They just sampled 292,966. So that would make it a population, a sample mean. Should we expect the mean tax, X bar, of the 292,966 to be exactly the same as the mean tax of all the individual returns? No, you shouldn't. I mean, simply put, no, because think about it. There's all sorts of values we could put in there. Maybe out of that 292,000, you chose 200,000 poorer people, or people on the low income end of the socioeconomic ladder. Or suppose you chose 200,000 that were up in the upper end of the economic ladder. Well, your sample's going to be misrepresented a little bit, okay? So you shouldn't expect it to be exactly the same because of sampling error. Excuse me with this I have in my mouth. I have a cough drop, so I don't cough all the time in your face while I'm doing this video. So if you hear something weird, I'm sorry. Okay, so how can we answer questions about sampling error? For instance, is the sample mean tax, X bar, reported by the IRS likely to be within $100 of the mean tax mu? Well, the quick answer to that is in order to be able to determine this, whether it's within $100, you would need to know what is the mean of all the possible samples. Well, that means we need to know something about this distribution. That means we need to know the sample mean, the sampling distribution of the sample mean. The sampling distribution of the sample mean. So what is this? Well, for a variable x and a given sample size, the distribution of the variable x bar is called the sampling distribution of the sample mean. In statistics, the following phrases are synonymous: sampling distribution of the sample mean, distribution of the variable x, distribution of all possible sample means of a given sample size. I say that because you may hear me say it in all these ways. You may read it in all these ways. So make sure you mark this and make a note of the different ways we can ask for the sampling distribution of the sample mean. So let's look at an example. Suppose that the population of interest consists of 5 starting players on a men's basketball team who we'll call A, B, C, D, and E. Further, suppose that the variable of interest is height in inches. So this table on the right gives us the 5 players and the height in inches. Alright, so what we want to do is we want to obtain the sampling distribution of the sample mean of sizes 2. Well, what's that mean? That means what we want to do is we want to determine what is the mean of each sample of size 2. Well, what are all the samples? How many different samples, how many different ways could we sample 2 of these players from these 5? Where I could sample player A, player B, AC, AD, AE. I could sample BC, BD, BE. I could sample CD and CE. And I could also sample DE. These are all the ways I could sample 2 out of these 5. Alright, well, when I do that, what are the heights? Well, for A and B, it's 76 and 78. For A and C, it's 76 and 79. 76 and 81. 76 and 86. For B and C, it's 78 and 79. 78 and 81. And 78 and 86. Well, for CD, it's going to be 79 and 81, 79 and 86, and for DE, it's just going to be 81 and 86. Now, what is the sampling distribution of the sample mean? Well, that's where we take the mean of each of these individual samples. So if I take the mean of 76 and 78, the sample mean, of course, is x bar. That's going to be 77. 76 and 79, if I take the mean, 77 and a half. 76 and 81, 78 and a half. And if we continue down, we'll get the following. We'll get 81, 78 and a half. We'll get 79 and a half. We'll get 82, 80, 82 and a half, and we'll get 83 and a half. Okay, so these are all the sampling distributions of the sample mean of a size 2. Okay, now you'll want to make note of this. Okay, write this chart down, pause the video, write the chart down, label it samples of size 2, sampling distribution of the sample mean, because when we get into the next section, we'll need this table. Okay, so go ahead and write it down so you can access it and not when we get to the next video. Okay, so letter B. Make some observations about the sampling error when the mean height of the random sample of 2 players is used to estimate the population mean. Well, what is the first thing you need to know is what is the population mean? Well, in order to find the population mean, we need to find the mean of the population, which is simply this. Now, that's the population mean. So when you look at this, what do you notice? If you were to use any one of these to estimate that population mean, what would you notice? Well, the first thing I notice is there is only one of these that estimate it correctly. So that means only 1 out of 10, or 10%, estimate it correctly. That's the main observation. Okay, so obviously there's some sampling error there. Now, letter C says find the probability that for a sample size of 2, the sampling error is within 1 inch of 80. So in other words, we want to know how many of these are within 79 and 81. We want to know how many are within 1 inch of 80. 79 and 81. How many are between there? Well, we've already got one circled. We've got one that's 80. There's one that's 79 and a half. Excuse me. And there's one that's 81. So 3 out of 10, or 30%, are within 1 inch of the population mean. So you got a probability of 30%, or 3 out of 10, that are within 1 inch of the population mean. Alright, so let's proceed. Alright, so here's the same problem, but notice what I've done. I've already given you the table. Now, what's the difference in this table and the one we just drew? Well, hopefully you're screaming at the screen. And our sample size here is 4 instead of 2. So notice we have 4 samples. These are all the ways to get 4 samples. This is the sample means of those 4 samples. So this would be letter A. Okay, this would be the answer to the letter A. We just didn't draw it out ourselves since it was already drawn for you. All right, so letter B. What's some observations that you can tell right away using letter B? Well, some observations that I see right away is that none of these 5 samples equal 80. So 0 of the 5 are equal to the population mean. That's the first thing I noticed. So obviously there's some sampling error there. None of the 5 are equal to it. So letter C. What's the probability that we're within 1 inch of it? So again, what is the probability that we are within 1 inch? So from 79 to 81 of the population mean. And remember, the population mean was 80. So we have 1, 2, 3, 4. So 4 out of the 5 are within that 1 inch. So 4 out of 5, or 80%, are within 1 inch. Of the mean. Now, that's very interesting, isn't it? What did you notice there? When we went from a population size, a sample size of 2 to a sample size of 4, what do you notice about letter C? There were more that were closer to the mean, right? Even though we had none that equaled the mean, we did have 4 that were within 1 inch of the mean. So what that means is, as our sample, if you think of it as a normal curve, as our sample size gets bigger, that normal curve is getting smaller and smaller, which means that our data is getting grouped closer and closer together. So we're getting closer and closer to the number we need, which is the mean. Okay? Here's an example. This is the written out version. Look what happens. Just look at the dot plot here. Notice when the sample size is 1, notice how spread out it is. 2, we get a little closer. 3, a little closer. 4, a little closer. 5, there were only 5 in the population, and so there's only 1 dot, and that is our mean. The closer you get to the actual population, the closer you're going to get to that mean. So your data should become more and more tightly grouped. And you can see that in table form here. Okay, so, and look at the number of possible samples. They get bigger, then they get smaller again, and notice the percentages. So as we get bigger, we generally say that we get closer and closer to the mean as the sample size gets bigger. Thus, this statement: the larger the sample size, the smaller the sampling error tends to be in estimating a population mean by a sample mean. So the larger the sample size, the better. Now here's the problem. With these basketball players, we only had a population of size 5. So it was very easy for us to find the population mean. Now, in real life situations, most of the time, we do not know most of the time we don't know the population. We don't know how many are in the population because it's so big. So we have to develop other ways for being able to find this mean. And that's what we're going to do in section 7.2.